All right, and welcome again to yet another video for AP Statistics. Today we are looking at Chapter 22, which is all about comparing two proportions. We're still looking at this world of proportions. We're still talking about P's. We're still looking at so many of the same things. We're just doing a few little differences. First off, when we're talking about comparisons between two percentages, this is actually a lot more common than the questions about isolated percentages. We've been doing a lot of things looking at, well, is there an improvement in one store or in one type of a situation over another? But typically what we're looking at is multiple people and each of those individuals' results before and after either procedure or some sort of medication or some sort of a treatment. And a lot of times in order to do this, in order to see how two groups differ, we might give one group a treatment, like one group takes the medication whereas the other group takes the placebo. Or we could say, well, how was the person doing before the treatment versus how was that same person doing after? For example, what was their health before they enrolled into a specific program and how was it after? Anytime you're looking at non-independent events, you're comparing proportions. If we were comparing survey results from two populations or comparing responses when two treatments are in an experiment, what we can do is we can either create a two proportion confidence interval if I'm trying to start with a sample and figure out where I think the population would be, or to start with a two proportion hypothesis test, which is where I think this is what the truth is, and you know what, I'm going to use my sample to evaluate the validity of that statement. Now, pretty much everything that we're going to do is going to be similar to what we did with one sample or with one proportion. So all of those things that we did with a one proportion z-test or a one proportion z-interval are going to be the same, but there is one difference, one big difference, and that is we have to define a new random variable. Now this is a little bit what's covered in some of the chapters that we had previously skipped, but that's not going to be a big deal. You just have to understand that the new sample, the sample that is defined as the difference between two groups, is defined as the sample of men minus the sample of women. Whichever order you want to define that in, you have to set it up first. So that's your first step. When you're comparing two proportions, either one individual before and after, or two similar groups, one with a treatment and one with a placebo, you have to define the new random variable, your new sample set. And that is the difference between the two groups, men versus women. And for example, plants receiving a fertilizer versus those not receiving fertilizer. So we've got treatment versus control, or treatment versus placebo. You have to, in order to do this, you have to find the average proportion and the average standard deviation for this new random variable, this new one group made up of two separate groups. Now, this is something we haven't talked too much about. When we're dealing with two separate groups, standard deviations themselves don't add up, but variances do. Variances, that's the square root, that's the standard deviation squared. The standard deviations actually follow pretty much what looks like the Pythagorean theorem. And this is what it looks like. These are the computations that you need to understand for confidence intervals involving two proportions. So if we go through and we say, okay, conditions met, proceed with a two proportion z-interval. First thing you need to see is that now the proportion that we're dealing with is the sample difference. So the proportion of one group minus the proportion of another group. So we're looking at the difference between the two proportions. The standard error, or how much variation there is between those two groups, is found by, and I want you to pay close attention to this, the square root of the sum of p hat q hat 1 over n1 plus p hat q hat 2 over n2. So basically this is the inside portion of the standard error for your first group plus the standard error for your second group. And therefore putting that all together into our confidence interval, the sample difference, or p hat 1 minus p hat 2, plus or minus your z-score, your critical value, remember we found that using inverse norm, times the standard error of the difference, which is this guy right here. Now the typical hypothesis test for the difference in two proportions is again that there is no change. Remember, your null hypothesis is that nothing has changed. So that would mean between the two groups there is no change. Sometimes they write this as P1 equals P2. Sometimes they'll write this as P1 minus P2 equals 0. But again, it's always important that you define what each of those values stand for. Now, when you use a hypothesis test talking about the differences between two groups, you're starting with the idea that there is no difference. That means the standard deviations for each proportion are exactly the same. And if that's the case, we combine or pool our counts to get one overall proportion. It's kind of like the idea of, I don't know, poker. You're gambling. Everybody pools their money into one big bin. Since there are no differences, we pool it together. And so the calculations that you need for a hypothesis test using a two-proportion z-test, the pooled proportion, so again, this is what you use for a hypothesis test. P starts with the number of successes, p hat pooled, the number of successes in the first event, plus the number of successes in the second event, so that's your total number of successes, divided by your total number of events, sample sizes added. The standard error is a little different as well. It is the square root of your pooled proportion times the Q pooled proportion times the square root of 1 over n1 plus 1 over n2. Sometimes what they'll do with this is they'll say p hat pooled, q hat pooled over p hat pooled, q hat pooled, but it doesn't really matter. And then the z-score again deals with that pooled proportion difference minus 0, because in a hypothesis test you're always assuming that your null hypothesis is that there is no difference. That's what that comes from, the difference between the null and your standard error of the pooled. So what you're looking at for a hypothesis test, let me go back up a little bit here. In a hypothesis test, you're always using the null hypothesis that the difference between the proportions is 0. That is always the case. Now if you remember back when we did a one proportion, we said that the z-score was the sample minus the null divided by the standard error. It just so happens the null here is 0. So when your conditions are met and your null hypothesis is true, this follows the exact same wording, the exact same usage that we had before. That means if there is no difference between the groups, the likelihood that we saw the outcome that we got is represented by the p-value. And we use the normal model to find that p-value. So we get to finish it up with this statement. I am blank % confident that the proportion of whatever your population that you're talking about is between, and this is what you get, higher or lower than the proportion of whatever you started with. So let me go back a little bit. We have a couple of different things here. For a confidence interval with two proportions, the p-hat that you use for the confidence interval is the difference between your separate proportions, the proportions themselves. Success in the first group divided by the success in the number of elements minus the success in the second group divided by its number of elements. They're separate proportions. The standard error for your pooled difference, you have to deal with each of them separately, but the square root encompasses the sum. And those pieces make up your confidence interval. But when you're looking at a hypothesis test, in which case the null is always that the difference is 0, that is always the null, the P that you're going to use in the hypothesis test, it assumes that there is no difference, and so we can just put together the total number of successes divided by the total number of outcomes, because the null assumes that there is no difference, so we can find it all at the same time. The standard error takes that pooled value and times the square root of that pooled success and failure times the square root of 1 over the sample size plus 1 over the sample size. And you use these two values in computing your z-score. So hopefully, again, you've noticed the difference. When you're talking about hypothesis tests, you pool them together and you use the pooled value. When you're talking about a confidence interval, you use them separately and you calculate them separately. And we always use the statement, I am blank % confident that the proportion of whatever is between whatever your interval that you get, higher or lower than the proportion of 1. So one population is between your interval, higher or lower, and you'd have to select one of those, than the proportion of the second group. Always putting in context. So the assumption and conditions for a 2-proportion z-test or z-interval. Number 1, again, it has to be random. Each selection has to be random from the next, and it has to be selected from a homogeneous population. Homogeneous meaning a nicely equally mixed. You're not going to have groups of one or another, so you're not going to be more likely to pick one thing than another, or something done by a random generator like an SRS. Second thing, you still have the independence assumptions, which are met by your 10% condition. Okay, again, if you're polling people or things, the sample should not be more than 10% of the total. Now, this is a key thing here. In order to do a 2-proportion z-test or z-interval, they have to be independent groups. Group A has to be completely independent from Group B. In other words, the group that receives the placebo has to be completely independent from the group that receives the treatment. Absolutely a must. Next thing, each of your independent groups have to pass the success-failure condition. Each group has to have N1P1 and N1Q1 greater than 10. Both groups must be big enough. And if you have those, you get to proceed with caution. Now, if we're thinking about this and we're talking about husbands and wives, or before and after, this is a little bit different. Those fail the independent assumption. Technically speaking, husbands and wives are not the same person, but they're together because they share similar characteristics. They have similar viewpoints. So one is not completely independent of each other. And before and after treatments, again, that fails because it's the same individual. So if you fail your independent group assumption, you cannot do a difference of proportions. It's actually a little bit different. It's a slight tweak. We still will be able to do a comparison, just not using these methods. No matter what, you must always state these conditions. Because number one, statistics is more about the work than what it is about the answer. You have to be able to justify your work, put it in context before you go any further. So in summary, from everything that we've talked about here, you need to understand that our assumptions and conditions are primarily the same: randomization, independence, and sample size. But some of the things that are different is now the groups have to be independent of each other. There must be no linkage between each of the two groups that we're dealing with, and each of the groups must meet the success-failure condition. Also, we had 2 main new formulas. We had our formula set for confidence intervals. And remember, in a confidence interval, as it is centered around the sample sizes, we're dealing strictly with the samples. So we're talking about the difference between two proportions. So it's the difference between the proportions. We're talking about the difference between two proportions. So it's the standard error of those two proportions. And again, this guy is always going to be plus. It comes back to the Pythagorean theorem. If I square anything, it always ends up being positive. And we'll discuss that further in a different unit. Also, hypothesis test. For a hypothesis test, since it's based off of the idea that there is no difference between the proportions, that's my null, we get to pool them together in order to find a new proportion. The standard error is also pooled, but we have to take into consideration the sample size. And the z-score uses those two results. So please, please, please come prepared to class, understanding, if not how to use the formulas, what the formulas are, and what your conditions are. Specifically the fact that your two groups must be independent of each other. Because if the groups are not independent of each other, they actually have a completely separate equation and method for solving. All right, see you guys next time.